Another application of derivatives is applied optimization problems. And these were actually probably my favorite when I was in college. They gave me a little bit of trouble. Once you get the trick of them, you should be pretty good. So before, one of the common applications of calculus was calculating the min or the maximum value of a function. That's what we did in section 4.3 on absolute extrema. But in the real world, companies want to know how to minimize production or maximize revenue. And we can do that by solving applied optimization problems. So let's take a look at this example. So if I'm maximizing the area of a garden, and I have a rectangular garden that is going to be constructed using 100 feet of wire, and what I need to do is I need to determine the dimensions that would create the maximum garden area. Okay, so how do I do that? So the first thing I know is that I have 2x and 2y, and that adds up to the 100 feet of wire I have. I also know that the area is what I'm trying to maximum. Recall that the area is just of a rectangle is just going to be x times y. So we can rewrite the area just in terms of x. So why don't we solve this first problem for y? So I have just one y though because I have only 3 walls. So I have y equals negative 2x plus 100. Now I can rewrite area just with x. So area equals x times negative 2x plus 100. I'm going to simplify that to negative 2x squared plus 100x. So now we have our function. But before we maximize this function, we need to determine our domain. Okay? So we need both sides to be positive. So we know that x has to be greater than 0 and y has to be greater than 0, right? And since y equals 100 minus 2x, the biggest value that x could take on is 50. So x must also be less than 50. So therefore, we're going to determine the maximum value over our x values, which are from our interval will be from 0 to 50. But we don't know if it has a max over an open interval, okay? We do know it will have an absolute max and minimum over a closed interval. So we're going to examine it over this closed interval. So let's put some brackets and make this closed. So let's remember that extreme values occur at the endpoints. So I'm going to go ahead and solve this problem. I'm going to plug in to my function for y, my function for a of x. I'm going to plug in 0 and I'm going to plug in 50. So I have a of 0 is going to give us 0. And what happens if a is 50? And that means y equals 100. And if I have x is 50, that's also be 0 because that means y equals 0. So we found our endpoints. Now I need to find our critical points. And I do that by taking the derivative. So I'm going to take the derivative of this function here. I have a prime of x equals negative 4x plus 100. So if I solve for x and set that equal to 0, I get x equals 25. So when x equals 25, I have that y equals 100 minus 2 times 25, which gives us 50. So when x is 25, y is 50. So in order to maximize our garden, right, the area of the garden is going to be 25, 50, 25. So our area would be 25 times 50, which is 1,250 square feet. So that's would be our maximized area of our rectangular garden. Now, what if we have 200 feet of fencing? 200 feet of fencing changes things up a little bit, but not too much. So let's go ahead and open this up on a new page. So if I have 200 feet of fencing, then how big could my garden grow? So I know that area equals x times y. I know that I have 2x plus y. That's going to be the area around my garden, except there's a stone wall over here, right? This is a stone wall. And that equals 200. That means y equals negative 2x plus 200. And we want to get area just in terms of x, so I have area equals x, and I'm substituting for y, negative 2x plus 200. So I get that the area of x, because now it's just defined in x, is negative 2x squared plus 200. I know that my x value has to be greater than 0, my y value has to be greater than 0. If I have x equal to 0, that means y is going to be 200. Now if I have x equal, y equal to 0, it means x has to be 100, so x is less than 100. So now we have, it's defined over this interval, so we're going to examine it over 0 to 100. So I'm going to take the derivative of my new function for area. I get negative 4x plus 200. I'm going to go ahead and set this equal to 0 and solve for x. That gives me x equals 50. So in order to optimize the area of this garden, I have x equals 50, y equals 100, and my area would be 5,500 feet squared. So what are some steps when it comes to an optimization problem? So the first thing we want to make sure we do is we want to introduce all variables. When applicable, draw a picture and label all your variables. This is what I love to do. This is really important so you can keep track of all that you're working with. Next, you need to determine which quantities to be maximized and minimized, okay? And what the range of those variables can, the range of the other variables can take on if you can determine that at this time. Next, we need to write any equations relating our independent variables in the formula from step 3. We did that last time when we were working with area. We had the length of the wire variable and the area. Then I need to identify the domain, right? All possible x values that my function can take on, and locate our maximum or minimum values, right? It depends if we're maximizing or minimizing. This step looks at our critical points, right, which we find by evaluating the function at the endpoints. So let's do another example where we're going to maximize the volume of a box. So an open top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square, right? See right here, we're removing a little square from each corner and folding up the flaps on the sides. What size squares should be cut out of the corner in order to get the maximum volume? So here we're maximizing again. All right, so what do we know? Well, I know that volume of a box is length times width times height. And I know that from each corner, I'm going to be taking out just a little bit. So let's label that x. So I know that my volume is going to be 24 minus 2x times 36 minus 2x times x, right? That's my height. X becomes my height. If I simplify this out, I get that volume defined by x equals 4x cubed minus 120x squared plus 864x, okay? Now I know that I need x to be greater than 0 or x to be less than 12, because if x was less than 12, right, because this is 24 inches, we'd be folding our box in half, and then it'd have an area of 0. We don't want to do that. So we're going to have this interval, and we're going to examine it over the closed interval from 0 to 12. So first I'm going to take the derivative. Exciting, I know. So I have the derivative of our volume equation gives me 12x squared minus 240x plus 864. I'm then going to factor out the greatest common factor, which in this case is a 12. And then what I'm going to do, instead of factoring this, because this isn't going to factor nicely, I need to use the quadratic formula. So I have x equals, sorry, I've got to do this up here, but I'll switch to green. Follow the green. X equals negative b plus or minus the square root of b squared minus 4ac. So that's 1 times 70 all over 2a. So I get 20 plus or minus the square root of 20 squared, which is 400, minus 4 times 70 is 280. So that leaves me with 120 all over 2a, which is just 2. Square root of 120. And 20 is... 120 is 4 times 3 times 2 times 5. So the greatest common factor is 2. So I've got 20 plus or minus 2 square root of 30 divided by 2. So I have 10 plus or minus the square root of 30. That is my height. But this is not in our domain, right? 10 plus the square root of 30 is not my domain. So we're just going to have 10 minus the square root of 30. Is the value of x we'd cut out in order to maximize our volume.